Okay, so we've been talking about how things go together into different molecules to give us different shapes. These are things that we will have a quiz on tomorrow. Fun times. I think I said that yesterday, right? We'll see where we're at the end of the day. It might be on the quiz tomorrow, if we feel like it could be. And I think it probably will be able to. So today we are going to talk about how we can now use the shapes. So we're going to we've talked about how things go together. We talked about how we can determine the shape by looking at how it goes together. Today we're going to go back a little bit to electronegativity. We're going to talk about electronegativity and what that tells us about the bonds of these molecules. And then we're going to combine that with our ideas about shapes to look at some of the properties of these different molecules. So we looked at how electrons are shared, and that's how we're going to start. So for a quick review, some dogs teaching chemistry.
Welcome to Dogs Teaching Chemistry. Our first lesson is chemical bonding. Chemical bonds are what holds atoms together. A chemical bond is an attraction between atoms that allows the formation of a chemical chain. The electrons that participate in a chemical bond are called valence electrons. These are electrons that are found in an atom's outermost shell. Let's take a look at the types of chemical bonds that can be formed between atoms. An ionic bond is formed when one of the atoms engages an electron with the other atom. This results in a positively charged ion, called a cation, and a negatively charged ion, called an anion. Positive and negative attract, and the result is an ionic bond. Covalent chemical bonds involve the sharing of a pair of valence electrons by two atoms. There's also what is called polar covalent bonds. These are covalent bonds in which the sharing of the electron pair is unequal. The result is a bond where the electron pair is displaced towards a more electronegative atom. Thanks for watching, and we'll see you guys next time.
This class must be mostly cat people, because usually when we watch it, there's a lot of awws. Okay, so we're going to look at first bond polarity and how we can determine the degree of electron sharing using electronegativity. So we can determine the polarity of the bond. So we can determine the degree of electron sharing in a bond using electronegativities. Now this is in a single bond. We know that there are molecules which can be made up of more than one bond. What this electronegativity model allows us to do is to compare just individual bonds within that molecule. And that's really what we're limited to. We can't look at the entire molecule and use electronegativities to determine the polarity of that molecule. But we can look at individual bonds and say, if I were to look at the bond, this bond in this molecule at this point in time, where are those electrons most likely to be found? And there is a continuum. So if we have the difference is 1.5 and above, it is an ionic bond. So if that difference is greater than 1.5 and above, that's an ionic bond. If it's between 1.5 and 0.5, those electrons are shared in what's called a polar covalent bond. And if it's from 0.5 to 0, we say that is pretty close to nonpolar covalent. So that is kind of our degree of electron sharing that we can have. Again, if it's greater than 1.5, that's going to be an ionic bond. If the difference is 1.5 to 0.5, we say that those electrons are still shared, but one atom is a little bit stronger than the other atom, meaning that those electrons are going to be more attracted to that atom. They're still shared, but they're closer to the more electronegative atom. If it's less than 0.5, now that difference is not very much. So those electrons are shared pretty equally in between both of those atoms that are forming that bond. So that's kind of the difference as we model it. With me so far? Okay, so an ionic bond, for example, we have something like a bond between sodium and we have a bond between chlorine. Sodium has an electronegativity of 0.9. Chlorine has an electronegativity of 3.2. The difference between those is 2.3. Yeah, I could do that in my head too. So the difference is 2.3, which means that it will be an ionic bond. It's greater than 1.5. Now, I would not draw this as forming covalent bonds, right? These are not going to share electrons. What happens to those electrons? Yeah, they're completely transferred. So that sodium ion loses an electron, and then that chloride gains an electron and fills its shell. Again, this is how we would draw ionic compounds. So we have a difference of 2.3. That is going to be an ionic bond. Sodium loses, chloride gains. Lewis diagram? I don't know. A dotty model? Like, what do you mean, what kind of model? Yeah, we just call them Lewis structures. And for ionic compounds, it's really that exciting. Like, it's just showing that ratio. So if it's 1 to 1, it's just 1 to 1. Showing that metals empty, non-metals fill. And then that's our model. We don't really draw ionic compounds like that very much because it's kind of a given. Like writing NaCl, we can fill in the blanks in our head. Kind of know what's going on. When we go to the other end of the spectrum and we look at something that's maybe non-polar covalent, we look at maybe a bond between chlorine. So we have Cl2, chlorine and chlorine forming a bond. The electronegativity of chlorine is 3.2. And this one's 3.2. The difference between that is 0. So chlorine has an electronegativity difference of 0. So these will form a bond. So chlorine will bond with another chlorine, but it's called a non-polar covalent bond. Those electrons are shared equally. That's what a low electronegativity difference means. When those two dogs were sharing those electrons, they're pretty much right in the middle. If I want to find those electrons, they're probably somewhere in this bond. They're not more towards one atom than the other. And for anything less than 0.5, so even if it's greater than 0, in order to be shared exactly equally, it has to be 0. If we have a slight difference, again, it will be closer to the more electronegative one, but that difference is so small that it's not very significant. It does become more significant when we look at polar covalent bonds. So this is between something maybe like carbon and hydrogen. That's a common one. So if I have a carbon-hydrogen bond in a molecule, carbon has an electronegativity of 2.6. Hydrogen has an electronegativity of 2.2. What? That's not a good example. I'm not going to do that. Sorry. Carbon-oxygen bond. Carbon-oxygen. Oxygen is 3.4. So that difference is 0.8. So that tells me that it's still less than 1.5. So it's still going to share electrons. It's not going to completely transfer electrons. But because the difference is greater than 0.5, that tells me that that electron sharing is going to be unequal. And we draw that with something called bond dipoles. So I take this carbon and I take this oxygen. Which one is more negative, more electronegative? Which one likes electrons more? Oxygen. So the way that I show that with a diagram is I make this my more positive one, and I show that the electrons are shared more towards the oxygen. So I draw in what's a vector, basically. In Science 10, you maybe did a little bit with vectors. They have both direction and magnitude. Oh yeah! You ever watch Despicable Me? He calls himself Vector because he's committing crimes with both direction and magnitude. And that's really what a vector is. So this has a direction and it has a magnitude. That 0.8 is kind of the magnitude, that's the difference, and the direction is towards the more electronegative one. Now that causes those electrons, yep. No, it's all, we always just do absolute values. Yeah. Yeah, like, we only care about the difference. We don't care about, like, we determine which way the electrons are going to be pulled based off of one that's more electronegative. Now, another way that we show this too is we also write which one's going to be slightly negative and which one's going to be slightly positive. The oxygen is more electronegative, so it's going to have a slight negative charge. Actually, I think I'm supposed to write that in front. It's a sigma. And this is going to be slight positive. This mathematically, what it means is less than 1. So if I look at sodium chloride, right, this is positive 1, this is negative 1. There is a complete charge difference. This has lost a complete electron. What this symbol means is that this is going to have a slightly negative charge because it has more electrons closer to it. This is going to be slightly positive because the electrons are more away from it. Does that kind of make sense? They're still shared in this bond, but they're probably like closer over on that side. Like somewhere over here is where those electrons are. So that causes this to be more negative and this to be more positive. Now, because there is not a complete transfer of electrons, we use this symbol. This symbol just means less than 1. So it is a negative charge, and this symbol means that that negative charge is a fraction of 1. It's less than 1. Sigma. Sigma, psi, delta psi. You ever do like step in? Sigma, ow. Sigma. That really hurt my ears because I have the microphone on. You'll hear it back on YouTube later if you want. Yeah, so it's just sigma. I don't know why they picked it, but they just decided that's going to be the symbol for fractional charges. So it really just means it is going to be slightly negative, but it's not going to be as negative as an ionic bond, which completely transfers it. Okay, so that's kind of our... yep. So this is only going to be used for looking at electron sharing in a single bond. So we're only ever going to use this model to compare one connection. I might look in a molecule and there might be a CO and then there might also be a Cl here or a Cc. I would analyze all of those attachments separately using these electronegativities. Okay. Right, we only use this for, like, it'll say, like, just for one of those bonds. So to look at just the one carbon and the one hydrogen, how would we classify that bond? Would it be ionic, polar covalent, or non-polar covalent? So again, these are sharing electrons. This is a complete transfer, and there's a continuum here. All the way from a complete transfer of one charge, so totally positive, totally negative, no transfer at all. So you'll notice we don't have these symbols here because one is not more negative than the other. They're exactly equal. Those electrons are shared in the middle. To this one, which is kind of a hybrid. Those electrons are more towards the negative one. We can draw it with this vector, and we can also identify which one is going to be more negative. This side will be more negative than that side. Okay? So that is bond polarity. Does that kind of make sense? It's really just using electronegativities to identify it, and that's what you'll do in those practice questions. Shane?
I don't know if you answered this, but do you have a negative vector?
We always draw them this way, just because it just looks cool. It's like, oh, this is a positive sign, and then it goes to the place that's more negative. I guess, I don't know. But you can have negative vectors though, yeah. But we just draw them that way. Okay, so you have some practice questions there. You're going to use your periodic table and your electronegativities to identify those bonds as being either ionic, polar covalent, or non-polar covalent. If it is a polar covalent bond, I want you to draw in these sigmas, so identify which atom would be more negative, which one would be more positive, based off of their electronegativities. Again, the higher the electronegativity, that one will be the more negative one. The lower electronegativity will be the more positive one, because the electrons are going to be pulled more towards the atom with the higher electronegativity.